without needles.
All right, who's ready?
I hate needles.
More probability. Yay! This is not that bad though, because it's mostly just restatement of the rules that you've learned in the last lesson, and a couple rules that generalize a little bit farther. So for example, we only learned how to find probability of A or B if the events were mutually exclusive, which is that nothing in common. Today we'll talk about what happens if they've got something in common. Okay, so the first rule is this complement rule, which we've discussed, I think, twice now. So if you know that the event A occurs, how can you find the probability that A does not occur?
Opposite of A.
Yeah, so A complement is the opposite of A. So what is P of A plus P of A complement? What do those have to add up to? 1. So that implies that P of A complement is 1 minus P of A, right? All I did there was took P of A away from both sides and just solved for P of A complement, right? So P of A is the chances that an event happens. P of A complement is chances that event does not happen. Okay. So I think we had this example yesterday, Monday, where you toss a coin 3 times, and we listed out the sample space. How many things were in that sample space? Do you remember? 8. It was 2 times 2 times 2, or 8 things. And they were things like heads, 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 right? Heads, heads, tails, etc., right? And there were 8 of those different combinations. Okay. So suppose the event A is getting all heads. Do you agree that the probability of that is 1/8?
Yes.
So there's actually one of those in there. So what is a complement then? If A is getting all heads, A complement is not getting all heads. Does that make sense? Like just the opposite exactly. Or you could say having at least one tail, or one flip that is a tail. Does that make sense? So what is the probability of that happening? What's the probability you have at least one tail, meaning 1 tail, 2 tails, or 3 tails? How'd you get that? 1 minus 1/8, exactly. You also could get that by looking at your list and counting, oh, there are 8 things that include tails, right? Or 7 things that include tails, right? But often it's easier to think about it in terms of, oh, it's 1 minus what I had because they're complementary events. Okay. Assuming all 365 days are equally likely, we're not going to talk about leap years, what is the probability that a stranger does not share your birthday?
364.
Okay, how about the probability that they do share? 1 in 365. Probability of no share is going to be 1 minus that, which is 364 out of 365. So do you see how both of those examples are complement rule things? Okay. Okay, rule 2 deals with ors, and I told you about rule 2b. That said, if you have events that are mutually exclusive, then P of A or B is P of A plus B of B. Now, how do you check if 2 events are mutually exclusive? What has to be true? They have nothing in common. Okay. Now, in general, if the events have stuff in common, you have to do this formula instead. P of A plus P of B minus P of A and B. And I think the best way to explain that is with a Venn diagram, because these are I think they're pretty helpful. So you have your event A, you have your event B. And you can think about the probability of A as the probability of the stuff in the A circle. Like as just think about it as the area of the A circle. And the probability of B as the stuff inside the B circle. And A and B is the stuff in both circles. Okay? So if you find P of A, that's this whole thing. Okay? If you find P of B, that's this whole thing. Does it make sense that P of A or B, that's like the area enclosed by both bubbles? Okay, so if I do the first bubble plus the second bubble, what's the problem? Yeah, what'd you do with the middle stuff? How many times did you count it?
Twice.
Counted it twice. That's why you must take away the middle stuff once to account for the overcountingness. Because you have events that land in both A and B. Like we had the example with the cards and the face cards and the hearts, right? You have some face cards that are face cards and hearts, and they land in the middle. They're in both. What does that picture look like if they're mutually exclusive?
The circles are not touching.
The circles are not touching. So there's A, there's B. And so in that case, what would P of A and B actually be?
0.
0. So technically, this formula is a special case of the first one. So you could really just memorize the first one and know that, oh, if P of A and B is 0, you just put in 0. And by memorize, I mean you get a note sheet, so, you know. But you still have to know how to use it, right?
So you want to put, so this left one is for 2B and the right one's for 2A.
The left one is for 2A, because there's overlapping. And this one's for 2B, because there's no overlapping. Mutually exclusive means no overlap. But do you really need two rules? The answer to that question is kind of like, technically, no. If A and B are mutually exclusive, if A, B are mutually, thank you, exclusive, P of A and B is equal to what? 0. And the first rule still works. That's the point. Okay.
So you just don't want to count the middle part at all?
For rule 2A, is that what we're looking at?
Yeah.
So for rule 2A, if you find P of A, that does like this thing.
Mm-hmm.
If you find P of B, that does this thing. And that middle gets counted when you do the red and do the purple. So what you've done is you've counted this middle part. That middle part got counted twice. That's why you have to take one of them away. Exactly, yep. Because there were two, you counted twice. You counted it once when you did the probability of A, once more again with this one, and you only want to count it once. That's why. Okay. So example 3, we have, suppose people are equally likely to be born on any day of the week. You meet a new friend and you ask her on what day of the week she was born. Like she's gonna know. But, we'll just pretend. What are these simple events in the sample space?
Day of the week.
Days of the week, so let's list them. Abbreviated, please. Sun, Mon, to, when, Thursday, Friday, you know, approximations, right? You probably should separate the Tuesday and Thursday somehow, and the Saturday and Sunday somehow. Or you could call them days 1 through 7, beginning with a Monday, whatever. So what's the probability of a weekend? Which really is probability of Saturday plus probability of Sunday, right? And there's no overlap, so those are mutually exclusive events, right? So that's 2/7. Let's add one thing to the bottom of this page because I think we had the one, I wanted the one with the hearts. So let's A be the event that you draw a heart. B, be the event you draw a face card from a deck of 52 cards. What's the probability of A or B? So, is the heart and face card thing, are those mutually exclusive things? No. So we're going to use the first rule, P of A plus P of B minus P of A and B. And then just consider each event separately. What are the chances that you draw a heart if you have a deck of cards?
13.
Out of 52. What are the chances that you draw a face card? 12 out of 52. And this last one is heart and face cards. So how many hearts are face cards?
3.
And then just go ahead and add. And I think you get 22 out of 52. We did that one last time, didn't we? Except for, I think that what we did instead of saying 12 out of 52, we took away the 3 we'd already counted, right? So that's how you do that problem using this rule that we learned today. Okay, which you could then reduce to 11/26, right? Okay. So Brett is off to college, and he's not in Alaska, so he's gonna have a roommate. He's not gonna live at home. No offense if you live at home, it's just more practical. In Alaska, there's one choice if you live in Fairbanks, so. And there are 1,000 additional male students, and one is gonna be randomly assigned to share Brett's dorm room. He's hoping it won't be somebody who likes to party or somebody who snores. And so somehow they got this table of values if you party or if you snore. So we're gonna use the table to find the probability that Brett will be assigned a roommate who either snores, likes to party, or if he's really unlucky, both.
Well, we actually have a survey at Res Life where you fill it out where it's like you're a night owl or early bird.
Yeah, I remember I filled those out when I was in school.
Maybe they took that data and put it together of what people filled out.
Okay, so let's let A equals likes to party. B equals snores, just to like sort of have shorter stuff here. So we want to find P of A or B, right? Party or snores, and that includes both. Like as in that or implies you could be either one or the other or both.
Looks like we got both.
It just means you're really, really not lucky. So that's P of A plus P of B minus P of A and B. Okay. So, is everyone all right with the application of the rule, what A and B stand for? All right, so how many people total in this table like to party? Out of how many people total? 1,000. See, that's the whole, this row, right? That's all the partiers. How many snorers do we have?
350.
Out of 1,000 again, right? And how many people are both snorers and partiers? 150. Okay, so 250 plus 350 is
600.
and then minus 150 is 450 out of 1,000, or 45 out of 100, which as a decimal is 0.45. So pretty much Brett has a 50-50 chance to have a roommate who likes to party, likes snores, or does both. He should buy some earplugs. Or, anyway. As if it wasn't random, right? Because Res Life does try to push people with similar needs.
There is room swaps.
There is room swaps, yep. So does that make sense, though, how we found those numbers? Okay. So the probability that more events occur together. I like moat better too, but that's not a word, I think. Is moat a word?
Like castle note.
But it's this M-O-A-T, that, yeah.
It's like a really small, like motor.
Okay, okay. Spell check didn't catch us, so it must be a word. I'll use it in Scrabble. So in general, the probability for independent events. Okay, so if you have independent events, we learned this rule, right? Remember that? Yes, vaguely. Okay. In general, if you want to find the probability of A and B, you can use either of these two things. Find the probability of A times probability of B given A, or probability of B times probability of A given B. And which one you have depends on the context. This is probability of B given A means what the chances B occurs knowing A occurs. What's the chances A occurs knowing B occurs. So, and the extension, this last one, says if you have lots of independent events, if you have many, 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 many ands in a row, you can apply this rule repeatedly. Does that idea make sense? That's assuming that they're independent. And when you're dealing with independence, you will either be able to use those rules that I told you last time to check, or the problem will tell you that these events are independent. And so how did you check independence last time? How did you do it? What was our most common method?
You had to do the math, see if B equals the same thing.
You had to do P of A and B, right? You had to find that. And then you had to find P of A times P of B, and what had to be true for them to be equal, or then be independent, they had to be the same, okay? So if these equal, that implies independent. That's the way to check. I think there was also a way using these rules as well. I think that was true if, whatever, okay. But the most common one we used was that rule 3B thing. Okay. So a brand of cereal contains a prize in each box. That's how they get you to buy it for your kids, right? No, not that way. Okay. For yourself? Yeah, exactly. I want the prize in the box. Okay, and there are 5 possible prizes, and each of the prizes is equally likely to be in any box. So if you purchase 2 boxes, what's the probability that you receive the same prize in both boxes? So first, let's figure out how many total things in the sample space. Sample space has, someone said it. How many prizes can go in the first box? Well, how many choices for the prize? 5 choices. How many choices for the next box? Also 5. So that'd be 25 total combinations. And that does include some kind of order, like, you know, a Beanie Baby in the first one, and then a race car in the second one. They're counted separately, but anyhow, 25 different events. If you purchase 2 boxes, what's the probability that you receive the same prize in both boxes? 1/5. Yeah, that's prize 1-1, 2-2, 3-3, 4-4, 5-5, right? Calling them like prizes 1 through 5, for example. So there are 5 ways out of 25 total, or 1/5. Okay, part B. If you purchase 2 boxes, what's the chances that you receive 2 different prizes? How is that related to A?
You subtract those ones.
That's the opposite. That's like saying P of not same is 1 minus the probability of the same. So 1 minus 1/5 or 4/5, which you guys meant, right? Yeah.
So like on the test, if we were to write P of different, would you get
That's
what
the
we're trying to
same.
do?
Yeah, definitely. I'll also on the test probably also give them letters, like say let event A be blah, so you can just write P of A equals, or P of A complement, then you could use. So if you also want to define them and say A is equal to the event, you get the same prize, then you could use A complement in part B.
Okay.
Okay. So Julie is taking English and history. Suppose that, I don't know why I have an extra at. Suppose that, no, at the outside of the term, our probabilities of getting A's are 0.7 for English class, 0.6 for history, and grade of A in both classes is 0.5. Are those events independent? Yes or no? How would you check? Don't rely on intuition. What would you use?
P of A.
Uh-huh.
B.
P of A and B. Okay, so let's say that event A is A in English. Event B is A in history. So did the problem tell you what P of A and B is?
Yes.
Yeah, what is it? 0.5. Okay. And then find P of A times P of B. So what's P of A? 0.7. What's P of B? 0.6, which equals 0.42, right? So since P of A and B is not equal to PA times PB, the events are what? Are not independent or are dependent. Okay. So yeah, that's how you should check independence. All right, use the addition rule for events, rule 2, to find the probability that Julie will get at least one A between her English and history classes. So an A in English, A in history, or both. So that's P of A or B, right? So what's the formula we use for that? Uh-huh.
Minus P of A and B.
Great. P of A plus P of B minus P of A and B. So what's P of A? 0.7. P of B is, and you could see there, if you forgot the next part, you would get something that was bigger than 1, which would make no sense, right? Okay, and then minus 0.5. So the probability comes out to be
0.8.
So good chances of getting at least one A. This next one you guys have? High school in small town? Okay. A high school in a small town always has its homecoming day and parade on the first Saturday in October. From historical records, it has been determined that the probability of rain during the parade is 0.15. Suppose you go to this high school. What's the chances that it will not rain on the homecoming parade during your freshman year? Just once.
0.85.
1 minus 0.15 or 0.85. Does that make sense? That's just the complement rule, right?
It's the opposite of what they're saying here.
Yes, exactly. They said that the probability of rain is
That's what I
0.15. Yep. The chances that it won't rain is 1 minus that. Okay, and I think that they said that these, that's the next thing. Okay, what's the probability that it will not rain any of the homecoming parades during your 4 years at school? Now, I don't know if I said this, I think I didn't. You have to assume independence. And usually I'd be better and I would state, assuming the events are independent, and you know that that's true now, what's the probability that it will not rain? So that's the probability of not rain, and not rain. I should have made a shortcut, shouldn't I? Okay, I'm gonna erase this. Let's let R equal it rains. What event do we want then? R complement. There's no half rain. Either you feel a raindrop or you don't. No one said how hard. So what's the chances of R complement and R complement and R complement and R complement? Because I told you that those rules are, yeah?
I'm actually wondering, could you just multiply it 4 times, like whatever our complement is, multiply it so it's like and?
Yeah, that's what I was gonna get to. PR complement, PR complement, PR complement. That's what you were trying to say, right?
Or just
But I
say
say RC
RC
times
times 4.
Times 4?
Or to the power
No.
of 4?
To the power of 4, yes, okay? So the times 4, sure, to the power, to that, no. Not times 4 to the power of 4, yes. Okay, that's what you could say, the probability of R complement to the 4th power, yes. And the reason it's to the 4th power is that rule that you have, the rule that we used is rule 3b, which generalizes that independence rule. And the independence rule generalizes to multiplications, not additions, right? If you multiply something repeatedly, that's raising to a power. If they were adding, then it would be 4 times that number. Does that make sense? Okay, good. So that's gonna be 0.85 to the 4th, right?
Yep.
Which works out to be approximately 0.522. So that's rain never, right? As in none of the years that you're there. About a 50% chance you will never see a drop of rain in homecoming, okay? So what's the chances that it will rain at least once during the 4 years? And the tricky thing about this is it could rain your first year, your second year, your third year, 4th year, or your first and second and third, you know, see, there's lots of combinations. Unless you look at it the right way and you say it's the
Opposite.
It's the opposite. Yeah, P of rain at least once is 1 minus P of not rain at all. Those events are complements each other, right? Either you don't rain or you do rain sometimes. And the nice thing is this raining at least once encompasses all sorts of different combinations. It rains all 4 years. It rains only 1 of the years, or it rains 3 of the years, rains only 2 of the years, and only 1, and all different ways you can like move them around. So 1 minus 0.522 is 0.478. Okay. And so often with stuff like this, these problems are kind of doctored to work in parts and lead you to the answer. So watch out for stuff like complement rule things in homework.
How did you get that number?
How did I get, which one? 0.478?
Yeah.
I did 1 minus 0.522.
Why would it be like 422? Or?
Got to do a whole bunch of borrowing, right? So that becomes a 0, 9, 9, 10,
Never mind.
8,
Got it.
right? Okay, yeah. I mean, subtracting is not my forte, so I mean, like sometimes, also how I check, because I learned these things fast, is if you add these two numbers together, you should get back 1. So, yeah. Okay. Alrighty. So we already discussed this a little bit as well. A sample is drawn with replacement if sampled individuals are, what happens to them? They are returned or replaced. I think return probably is more accurate because like you put them back in the sample. A sample is drawn without replacement if sampled individuals are not returned.
Wow, vocabulary word.
Yes, for subsequent selection. Is that the vocabulary word? We'll use big words on you.
No, I was talking about return and not return.
Yeah, returned and not returned. Added back to the pool. Okay. So in each situation, explain whether the selection is made with replacement or without replacement. So five people are selected for extra security screening while boarding a particular flight. Are you going to sample the same person once or probably not sample the same person once? Probably not, right? That'd be sort of stupid. Although they do ask the same question like 5 times, right? So this is probably without replacement. My personal favorite is I'm getting on a flight to come back home, like from Russia, and they say, "Why are you going to the States?" I'm like, "I live there. Just let me home."
What's the point of it?
It's suspicious, isn't it? What did you buy in Sweden? I don't know, clothes. Okay, go through. Okay, how about 3 digits in the lottery? Now, this does depend on the lottery, but can lotteries usually have the same number more than once? Yeah, I think usually so. So it probably is with replacement. And I didn't have a TV for like 10 years, so I haven't watched lottery numbers being drawn for like ages and eons. But when they draw balls out of like a spinny thing, do they often put the balls back and then draw again? I don't know.
They're
Well, in
really, like,
bingo,
ball
they
balls
put 'em in that.
anymore. It like blows up with air, and then whichever one just gets
It's sucked out?
To
And they keep it, but then they do keep it out, don't they?
Yeah.
So I think you could probably justify either way with that one, depending on what lottery game you're playing. Some do it with, some do it without. Okay.
Oh.
All right, now, here is another rule to find those conditional probabilities. So the probability of B given A, you can find by doing P of A and B divided by P of A. And notice that when you flip-flop that A and B in the next one, what part of it changes? Just the denominator, and that's because having this say B and A is the same thing as A and B. Does that make sense? So how I remember this rule, and you don't have to memorize it because you get note sheets. I have a test in the next hour, and I have to remember this formula. This ends up in the denominator. And the numerators are both ands. That's how I remember how this works. So, for what it's worth. Okay. So here's a question where we're going to use that rule. Yes?
I was just gonna say, so the therefore always ends up. Never mind,
The given thing, the thing that's given, always ends up in the denominator. Yes, yep. B given A ends up in the denominator. A given B ends up in the denominator. Exactly. Okay. So suppose that in a class of 50 students, 3 students are asked to answer a question. Suppose one student is Constantine, that's my husband. What's the probability that Constantine is asked to answer the first question, given that he is chosen to answer one of the questions?
1/3.
Let's see, okay? Yeah, well, so once we know he's chosen to answer,
Yeah.
okay, well, I think it actually works out to be 1/3, but I want to use that rule to prove it, okay? Yeah. So event A is that he's chosen to answer. Event B is that he's chosen first. And yeah, once we know he's going to be chosen, the chances he's first definitely is 1 out of the 3 people. But let's use this rule to also verify that. So we want P of B given A. Does that make sense why I chose that direction? Because we're told he was chosen to answer a question, right? Okay, so that's P of A and B over which one? P of A. Okay, P of A and B is that he's chosen to answer and he's chosen first. So how many people are chosen to answer that are first?
One.
Just 1 out of how many? 50. And then that divided the probability of A, which is that he's chosen to answer in the first place, which is 3/50ths, which does work out to be 1/3, like you said. My question was way easier than I thought I'd made it.
I don't know.
Yeah, no, it's fine, but that's how you would use that rule. It also makes sense that once you know he's answering, there's only 3 spots to choose from, first, second, or third, so he's chosen first 1 out of 3 times, right? That's how Faith got it so quickly. I didn't think about that because I was silly. Okay.
So, like on the test, if we were able to do that, do we need to show that?
No, you can do the problem better than I can. I'll still give you full credit. I might go, what, for a second while I'm grading and try to figure out what you did, then I'll go, oh yeah, that was stupid. So, yeah, as in me stupid, not you stupid. Yeah. Okay, in a recent election, 60% of the voters were Republicans and 40% were not. Notice that not includes both Democrats and independents in this case, right? Because, it's not like they're 2 events. And of the Republicans, 90% voted for candidate X. And I forgot to add something in, so add this in, please. Of the non-Republicans, 30% voted for candidate X. And I think you're going to need that to solve some of these problems. That seems kind of, well, I mean, it could be a bunch of independents doing that, right? Yeah, okay. So consider a randomly selected voter and let A be the event that the voter is Republican and B be the event that they voted for candidate X. Find the following and describe what they mean. So P of B given A, that's the probability that you voted for X, given what's true. You're Republican. And that's a good enough explanation for me if it's good enough for you. And I think you were told that number.
90%.
90%, so 0.9, right? Okay. How about this one? Probability that you voted for candidate X, given that you are anyone else, i.e. not Republican, right? At least not declared. And I think I gave you that number too, didn't I? 0.3. And the book has a question like this that's quite similar, and I want to add in a part C where we're going to use those to do something, okay? So question C, what I want you to do is find probability of A and B. Probability you voted for candidate X and you're Republican. It's not the same as the A given B.
4%? 54?
Yes. How did you find that?
Out of 60%, 90% of them.
Okay, yeah, that's true. Yes.
Sorry.
No, it's okay. I was trying to use the rules. So let's use the rules and we'll talk about why yours is the same thing. It's not a problem. So the rule you have, that's rule 3A. Lets you change this into P of, let me just do it right, P of A, P of B given A. And P of A are the chances that you're Republican, which is 60%, so 0.6. And of those 60%, how many voted for Republicans? 90%. So that gives them 0.54. But what you were using without realizing it was that rule, right?
I totally know this.
Yes, yes. I mean, a lot of these rules are reasonably intuitive, yeah.
So I accidentally started doing the homework after this one,
Mm-hmm.
and I started solving some of these in the way she was doing it, but it seemed like the homework led me along that route.
I think you're fine. Like, what you were just doing was applying some intuition to it, and that's totally okay. Yep, the rules just formalize that intuition. That's all. Okay. All right, suppose that 4.9% of property crimes occur in rural areas, and 1.9% of property crimes are in rural areas and are burglaries. What percent of property crimes that are in rural areas are burglaries? Okay, so let's make up some events. R is equal to the probability the crime is in a rural area. Let B be the crime that the probability, or not the probability, the event, sorry. Crime is in a rural area. B be the fact that crime is a burglary. I just spelled that wrong. Whatever. What percent of property crimes that are in rural areas are burglaries? So that last part, what that's trying to tell you is that you want P of B given R. Does that make sense?
Did you just say why?
Yes, I totally can. What percent of property crimes that are in rural areas are burglaries? So it means you know that you're in a rural area, and you want to know what's the chances you're going to have a burglary.
So the crime, so it's B given R because we know that B is the crime.
Because we know that B is the crime, and the thing we know is happening, the thing we're given, is that we're in a rural area.
Wouldn't it be the 1.9?
No, that's the ones that are rural areas and they're burglaries. So that's like 1.9% of like all total crimes are both in rural areas and they're burglaries. But the thing is, in rural areas, crime might be kind of rare. So you're kind of the 1.9% looks at like a bigger pool. It looks at all crime that happens everywhere. So you have your whole big thing that is all crime, okay? And then over here in the little corner, that's your rural areas. And the things where and then in your crime thing, you have burglaries. Okay? Bugs, they're burglaries. But anyway, so the 1.9% is this little bit of overlap, but of the little rural box, it might be a bigger proportion. Does that make sense? It's a good question, though. Okay, so probability of B given R, well, that's going to be probability of B and R, right? Over probability of R. Yep. So what's the chances that you have a burglary and you're in a rural area? 0.019. And then P of R would be
0.049.
And it would actually be okay if you did 1.9 over 4.9 there. Like, it's going to work out the same. And you get 0.387. So burglaries make up almost 40% of the crimes that happen in rural areas. Does that idea make sense? And maybe different crimes happen inside of like large cities, possibly. That's what this is saying. So one of the hardest things with these questions can be like dissecting what is it I'm supposed to find? Like, how do I make that question into a like statement of math symbols that I know how to work with, right? How do I translate it into that math? Okay, one last one. Oh no, two last ones. Is this one your paper or not?
No.
Did I put it there? Okay, it is, okay. Suppose the probability of winning a particular casino game is 0.2 and is independent from one game to the next. If someone plays the game 4 times, what's the chances of winning at least once?
0.2 times 0.2 times 0.2.
Okay, so if I find 0.2 times 0.2 times 0.2 times 0.2, that's not right, but it's okay.
Oh,
That's the chance that you're gonna win.
oh,
Okay, that's the probability that you will win 4 times. Is that what I asked? No, okay. You wanna know what is the chance you're gonna win at least once. So once, twice, 3 times, 4 times, right? Does that make sense? All those possibilities.
or you could do it that way and then find the subtraction thing you would get.
It's not quite that way, but it's awfully close. You could find the probability that you don't win. There's only one way to not win ever, right? And what would we multiply then? What's the chances of not winning?
2 times.
0.8.
Oh,
Does that make sense? Because winning happens with probability 0.2, so not winning happens with probability 0.8, right? And 0.8 to the 4th power ends up working out to about 0.41, we'll say. So that's the probability that you're never going to win. What's the probability that you're going to win at least once? How is it related to not winning?
5,
It's 1 minus that number, right? It's the complement of this, right? So that's what, 0.59? Otherwise, you'd have to find the probability that you win all 4, win 2 of them in lots of different orders, because the winning thing could go either in the, you won 2, it could go here, here, there, there. That'd be a lot trickier, right? So it's much easier to look at this in terms of the complements. And in that one, it was just kind of to figure that was the rule.
you
And-
can start by finding the complement of winning right off the bat.
You could, yep. Exactly. Okay. All right, suppose that in a dorm room, the probability that there is a TV is 0.52, probability of a mini fridge is 0.38, and the probability of both is 0.21. So find the probability of no TV in a randomly selected dorm room.
0.48.
Is 1 minus 0.52, which is 0.48. That's just basic complement rule, right? Okay. Probability of a TV, fridge, or both. I'm going to call it T or F. So what rule do you use for that? P of, that's if it was and, plus,
P of
minus,
P of
yep. Got to be very careful about those ands and those ors. They mean something really sort of serious in this class. Because and means both, or means one or the other, or both. So what's the probability of there being a TV? 0.52. Probability of there being a fridge. And probability of that there's both. And you get that this is 0.69, I believe. 1. Yep. Okay. All right, and the last ones are those condition probabilities. What is the probability that there is a TV given that there's a fridge? So probability of T given fridge. So that becomes P of T and F over P of F. Exactly. Good job. So what's probability of TV and fridge?
0.21.
Divided by probability of fridge, which is
0.38.
and that comes out to be about 0.55. And it should kind of stem with what you think about life, right? Once you know someone has something, and chances they're gonna have more somethings. Oh, one more. That was TV given fridge. How about fridge given TV? So FNT, which is no different than T and F, right? Okay, over, so 0.21 over 0.52. That works out to be 0.404. The thing to notice on those is that they're not the same, okay? As in, when you flip the order in those conditional probabilities, you do not get the same result. It's not commutative, okay?
And then you
No
can
flip.
say at the end of there that, so if they have a fridge, they're more likely